Washing the dishes, cleaning up your living space, going out and getting groceries, and then getting stuck in traffic. These are all the mundane tasks we all have to do every now and then. But imagine a world where you didn't have to worry about any of that. Wouldn't that just be amazing? Imagine not having to put away your shirts or socks because you know that the next morning they'd be exactly where you want them. As amazing as that would be, the probability of that happening is unfortunately and basically zero. It wouldn't happen because of one commonly known physics law, the second law of thermodynamics, the law of entropy. Entropy is best characterized as disorder, since it's mainly used to describe how things tend to spread out, get mixed around, and diminish, with no way of getting back to how it was originally. Law of entropy can be explained as the thermal energy or heat of a system being dispersed over time, or in even shorter terms, energy disbursement. This relationship that entropy has with time and how it's a one-way process is strange, considering most everything in physics can be reversed. Projectile motion, for example, can be calculated for a ball with initial velocity to figure out where and how it's going to land. You could also take a snapshot of the ball just before it lands to get those final values, and you could calculate where it was thrown from and how fast. Another repeatable process is the combustion process that goes on in a car's engine. And this cycle repeats hundreds of times in quick succession for as long as the car is on. Now, both examples that have been explained are reversible and repeatable processes that can be found all over physics. So why does entropy have to be different? Entropy is different because of its two main qualities, irreversibility and disbursement. Let's talk about the irreversibility aspect. Imagine you're at the beach and you decide, I want to build a sandcastle. You go through all the proper steps to build an amazing sandcastle, and you fast forward a couple of hours and you're finished. Take a couple of steps back and you admire your work. What you might be admiring may be the technical skills it takes to make a great sandcastle, or maybe even the amount of effort you put in to showcase just how beautiful you made it. But the thing that I want to point out is the exact and specific arrangement that all of that sand is in. The sheer amount of sand that is before you is hard to comprehend when you really sit down and think about it. Let's imagine this. In 1 cubic meter of sand, there are around 1.3 billion grains of sand. And in one singular grain of sand, there are about 1 times 10 to the 18th, or sometimes even 20th atoms. So when you combine all of that together, you get that on the low end of things, there are about 1 times 10 to the 26 atoms that would have to be in perfect alignment to be in the shape of your sandcastle. And keep in mind, you wouldn't just have used 1 cubic meter of sand to make a grand sandcastle. You'd most likely use more. And when all of those numbers compound with each other, you'll see that the only reasonable outcome is that building a sandcastle is an irreversible process due to the sheer amount of particles that have to be in alignment and in proper order. A sandcastle will always turn into a lump of sand, but a random lump of sand will almost never turn into a sandcastle. That analogy helps with understanding the irreversibility aspect of entropy. Now let's talk about the disbursement part. How can energy flow in just one direction? Let's think about where us as humans and as inhabitants of the planet Earth get our energy. The sun. The sun is our main source of energy. It comes to us in very large ordered amounts. And of that energy, how much does the Earth radiate back? To figure that out, let's follow the energy and see where it goes. Once we get a large amount of energy from the sun, that energy is then absorbed by plants or biolife or anything that photosynthesizes. It's then stored in smaller bits of energy within that plant, and is then further dispersed and scattered whenever a herbivore comes along and wants to enjoy a nice meal. The scattering and disbursement of energy continues as the herbivore is then hunted by a predator who then enjoys their nice meal. And with each step along the way, the energy gets more and more spread out and dispersed. It then comes around to us, which provides us the necessary energy to live. And as we live, we work, and we do things that send energy back out into the universe. Those things like exhaust coming out from cars, factories, stores, and other various sources. All of these small things build up and end up being radiated back out into space. As bizarre as it might sound, we emit around the same amount of energy that the sun provides us, although not in the same capacity, since the sun gives us all the energy in one big deposit, we radiate it back in smaller spurts of energy with only a very small percentage that gets absorbed. Now that we see how energy moves in one direction and only goes from an ordered state to a disordered state, we can then relate that to the universe as its continuous expansion speeds up and up. When we go back to the very beginning, before the Big Bang, there was a hot, densely packed point of singularity that is seen as the most ordered form all of energy has ever been in. Once the Big Bang occurred, all of that uniform, densely packed energy spread out in an instant and continues to do so even today. With the continued expansion of the universe, the energy also spreads out and even takes longer to get to where it needs to go since the space between everything in the universe also expands. The expansion of the universe isn't a constant rate, but an accelerating rate that keeps getting faster and faster, cooling the universe as a side effect. As the energy keeps spreading, increasing entropy, we see how one way this flow is. This will keep happening over and over and over, and there will continue to be energy that dissipates further into smaller and smaller chunks. It will have a hard time getting to where it needs to, such as light radiating from a sun to a nearby planet. Over time, that nearby planet won't be as close as it once was, causing that bit of energy that it receives from its sun to take longer to arrive or not even arrive at all. Once it gets to that point where entropy can't get any higher because all of it is so spread out that it can't interact with each other, that means that the universe has reached an equilibrium, simply by being too expanded. Once it's reached this equilibrium, then nothing will change. And when nothing changes, nothing will happen. That is the heat death of the universe, and its most widely accepted way our universe will meet its end. It's dubbed the heat death of the universe because everything in the universe will reach a stability point where there is no more free thermodynamic energy. But we still have a long way to go. Till then, let's keep building our sandcastles.